In this video, we're going to look at the graphs of cosecant and secant. For cosecant graph, y equals cosecant x, it's important to remember that cosecant is the reciprocal of sine, so this is 1 over sine of x. Since it's related to sine, our period is 2 pi. And it's undefined when sine of x equals 0. When our functions are undefined, that's when we're going to see those vertical asymptotes. So in the previous video, when we looked at tangent and cotangent and we had those vertical asymptotes, we're going to have them here in cosecant and in secant. Actually, we're going to build our table a little different. We're going to use those same values for x for our landmark points that we used for sine of x. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And let's first start by looking at the value of sine of x at these. So you could reference back to our table of values from a previous video. We also have seen these values in our unit circle and in other tables. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And sine of 2 pi is 0. So using this and thinking about the reciprocal to find cosecant of these values, cosecant of 0 is going to be undefined. Cosecant at pi over 2 is going to be 1. Cosecant at pi is undefined. Cosecant at -3 pi over 2 is -1. And cosecant at 2 pi is undefined. So I'm going to start by marking my period of 2 pi. Because we're just like we did before, we're going to divide that into 4 equal parts. So starting with halves. So here's pi. This is pi over 4. I'm sorry, pi over 2. And this is 3 pi over 2. We have our asymptotes at 0, at pi, and at 2 pi. Now, I'm going to sketch on this graph in a lighter color, the graph of sine x. So sine, thinking of 1 and -1. Sine started at our midline, went up to our maximum, back to our midline, down to our minimum, back to our midline. So sine looks like this. And what we're going to see with our cosecant graph is that we still have those points at pi over 2, 1, and 3 pi over 2, -1. But cosecant is actually going to mirror that sine function, but bounded between those asymptotes. So I've shown one graph of cosecant x in black, and I'm going to go ahead and erase this graph in blue just so it doesn't confuse us. But just to illustrate how we can see that graph of cosecant x from our graph of sine x. So there's our graph of cosecant x. Thinking about secant of x, this is the reciprocal of cosine x, so 1 over cosine of x. Because it's related to cosine of x, that period is 2 pi. And it's going to be undefined when cosine x equals 0. I'm going to set up my table of values over here on the right-hand side. So again, thinking about x, then cosine of x, then secant of x. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. Setting up the reciprocals of those to find the value of secant x. Secant of 0 is 1. Secant at pi over 2 is undefined. So we're going to have a vertical asymptote at pi over 2. Secant of pi is going to be -1. Secant of 3 pi over 2 is undefined. And secant of 2 pi is going to be 1. So setting up our graph, here's 2 pi. Dividing that into 4 equal segments. Here's pi, pi over 2, 3 pi over 2. We're going to graph our asymptotes at pi over 2, 3 pi over 2. And I am going to show one more asymptote. It's going to be down here at negative pi over 2, just so I can show the continuation of this graph a little bit. We don't get it cut off. And now I'm going to sketch that graph of cosine, just like I did for our first graph. So here's 1, here's -1. Cosine starts at our max at 0, goes to the midline, minimum, midline, maximum. So here's our graph of cosine. When we graph secant, we're going to have points at 0, 1, pi, -1, 2 pi, 1. And we're going to mirror that graph of cosine, staying within the bounds of the vertical asymptotes. So we're going to have this parabolic shape there, another parabolic shape there, and then there will be one over here as well. Looking at these two graphs, they're very similar, just like sine and cosine are very similar. They're just offset from one another. So for our cosecant graph, we have those asymptotes at 0, pi, 2 pi, and we don't intersect that vertical axis, that y-axis. If we look at the graph of secant, we do intersect that y-axis. So if we're starting to try to model an equation for a given graph, those are the things we want to keep in mind when we're trying to determine whether we want to start with cosecant or secant. Our transformations for these functions, again, I've given our two models just in terms of cosecant, but they behave the same for secant. We have form 1 and form 2. Again, for our graphs of cosecant and secant, we don't really have an amplitude, but they do help us identify those landmark points. So we're going to use that value of A to figure out what's the minimum of those parabolic branches that open up, what's the maximum of those parabolic branches that open down. B is going to be the frequency. Because we're related to sine and cosine, now we're back to that period of 2 pi for the parent function. So it determines the number of periods over 2 pi. So to calculate the period for any given equation, you're going to take 2 pi and divide it by that factor of B. Our phase shifts represent that horizontal shift. The way we determine the phase shifts is dependent on the form that the equation is given in. But we're going to use really the idea of that starting point, that asymptote, in order to identify that phase shift so that we can graph it. So the phase shift is going to be used to determine where that vertical asymptote for functions are located. We're going to set the argument equal to 0 for cosecant. Remember, that's our first asymptote for cosecant. And we're going to set it equal to pi over 2 for secant, because that's our first positive asymptote for secant. And then D is our midline, or the vertical shift. Looking at this, these parent functions, the midline is 0, but it's going to be halfway between that value, which is the minimum of those parabolic branches that open up, and the maximum of the parabolic branches that open down. All right, so we've had a lot of practice with graphing these periodic functions. So we're going to jump right into some more advanced examples for secant and cosecant here. We're going to graph y equals 2 plus 3 secant of 2x minus pi over 2 periods. So our amplitude here, that's the coefficient on secant, which is 3. Our midline is at 2. That's our factor that's being added to the function. Not our factor, the value that we're adding to the function. The period is going to be 2 pi divided by b, which is 2 here. Oops. So our period for this equation is pi. To find our first asymptote, we're going to take 2x minus pi, and we're going to set it equal to pi over 2. Again, the reason we're setting it equal to pi over 2 is because this is a function of secant. So that's our first positive asymptote in our parent function for secant. So adding pi to both sides, we get 2x is equal to 3 pi over 2. Dividing both sides by 2, x is equal to 3 pi over 4 is going to be our first vertical asymptote. Now I remembered that we do have a midline, that vertical shift up. So you notice I didn't center my horizontal axis in the middle of this grid. I'm going to start by marking my first asymptote at 3 pi over 4, going in units of pi over 4. Here's that first vertical asymptote. Our period is pi, so that's 4 pi over 4. So I'm going to go 1, 2, 3, 4 pi over 4 to the right to get my next asymptote, and I'm going to keep doing that. I'm also going to go to the left a little bit. So I'm going to go left 4 sections from 3 pi over 4. So 1, 2, 3. Here's, oops, negative pi over 4 is another asymptote. And then I'm going to go one more on the right because they wanted 2 periods for this graph. 1, 2, 3, 4. And we can label these by just counting multiples of pi over 4. So 3 pi over 4, 4, 5, 6. This is 7 pi over 4. 8, 9, 10, 11 pi over 4. We have those segments broken up into fourths. But we're really only going to use that middle point on this. Now let's mark the midline. The midline is going to be at 2. So I'm going to use pink for that as well. Sort of giving us this illusion of these bounds that we're going to use to help make our grid or make our graph. Now we want to think about this in terms of that parent function. So I'm going to go back to that parent function of secant. We start at that first point, that first minimum is on that axis. What we're really doing is we've just shifted this over slightly. So we still want that minimum of that parabolic shape to be to the left of this first asymptote. So this was that first asymptote, that pi over 2 asymptotes was just shifted over a little bit to the right, which means that instead of intersecting on the vertical axis, the y-axis, we're going to have that minimum of that first parabolic shape to be just to the right of that. Our amplitude is 3, so that's going to be used to figure out how far away from the midline we're going to set up those minimums and maximums for those parabolic branches. So 1, 2, 3, that gives us 1, 2, 3, 4, 5. And then going down 1, 2, 3, that's at -1. So my first landmark point is going to be halfway between -π/4 and 3π/4. So that's going to be 1π/4. It's going to be at 5. And it's going to yield a parabolic branch that opens up. My next landmark point is going to be halfway between 3π/4 and 7π/4, which is 5π/4. And that's going to have a maximum at -1. And it's going to be that parabolic shape that opens down. I just caught an error that I've made. So we're going to have to backtrack quite a bit, but I think this is a good illustration on how we make mistakes. When I was setting up the graph, I mentioned that the period was pi. But what I didn't think about or didn't remember was that one period is both the branch that opens up and the branch that opens down. So one of those branches should be over half of that pi, not a full pi. So we're going to have to erase and almost start over here. But not entirely. I think we'll be okay. And actually, I think we're really going to be okay. But I'm going to erase all those extra asymptotes I drew. Again, the entire period is going to be pi units, which means the distance between two asymptotes is going to be pi/2. So let's add that note here just so that we don't forget it in the future. And thinking that in terms of fourths, that's going to be 2π/4. So starting with that first asymptote of 3π/4, I'm going to go 2 to the left and 2 to the right to get my next asymptotes. So what I do want to point out is that now I'm actually adding the same asymptotes I already had. I just didn't have them divided up enough. So here's another asymptote. We're not going to graph in all of these, but I do just want to illustrate what we had wasn't, as far as our asymptotes go, they weren't wrong, but we didn't have enough of them. All right, so again, the idea that this 3π/4 was that very first positive asymptote, which means the branch that opens up is going to be just to the left of that, meaning halfway between 3π/4 and pi/4 is where we have the minimum of that first branch. So here's that first branch. Halfway between 3π/4 and 5π/4 is where we have the maximum of that second branch. So this is one period that we've drawn. Now we can continue on halfway between 5π/4 and 7π/4. So that's going to be 6π/4 or 3π/2. We're going to be at that minimum of the branch that opens up. Between 7π/4 and 9π/4 is 8π/4 or 2 pi. We have that maximum of the branch that opens down. And we can continue that pattern as we go. Again, I apologize for that error, but hopefully either you caught it yourself and you're thinking, man, what's she talking about? Or now you have this extra note to make sure that we don't forget about this in future examples. All right, so let's graph one more. Y equals 2 minus 4 cosecant of 1/2 x plus pi over 2 periods. So our amplitude is going to be 4. That negative means we're going to reflect. Now, when we have a midline as well, that reflection is actually about the midline. So actually, let's maybe write our midline first. Our midline is going to be 2 from this value of 2 being added to the function. And then we're going to reflect about the midline. So it's still going to be a vertical reflection, but we are going to reflect about whatever that midline is. So we'll start by graphing the midline, or at least marking it on our grid, and then using that to set up the graph. If we're thinking about that parent function of cosecant x, that cosecant x has our asymptotes at 0, pi, and 2 pi. And we would typically start with opening up. Since we're reflecting about the midline, we're actually going to start with that open down parabolic branch. All right, what's next? So we have our amplitude, we have our midline, we have our reflection. Let's talk about our period. The period is going to be 2 pi divided by the coefficient of x, which is 1/2, which is 4 pi. And as a reminder, that's the entire period. So that means that the distance between two asymptotes is going to be 4 pi divided by 2. I did not make that mistake this time. All right, so let's find our first asymptote. We're going to take our argument 1/2 x plus pi, and we're going to set it equal to 0. Again, that's that first asymptote from our parent function of cosecant x. So again, the 0 has to do with the fact that it's cosecant here. Let's make sure we noted that here. Yep, pi over 2 for secant. Good. All right, so let's start with our setting up our grid. Since we do have a midline, I'm going to make sure that I don't make my horizontal axis the very middle of my graph. My first asymptote is at 2 pi, and my period is 4 pi. So I'm just going to go by multiples of pi. Here's 2 pi. Here's negative 2 pi. So just exhausting labeling that horizontal axis. My midline is at 2. So let's start drawing some guidelines, the vertical asymptotes in that midline. Our first asymptote, oh, we didn't solve that. Sorry. I was using 2 pi as my example. So I'm going to take 1/2 x equals negative pi, solving that equation. And then x is equal to negative 2 pi. So it did work out okay, even though I kind of went out of order there. So my first asymptote's negative 2 pi. And the distance between asymptotes is going to be 2 pi. So then I have another asymptote here, another asymptote here, another asymptote here. And here's my midline at 2. Since my amplitude is 4, I'm going to go up 4 units from my midline and down 4 units from my midline to find those min and max values. So 1, 2, 3, 4. Here's 6. 1, 2, 3, 4, negative 2. So I really probably will need some extensions on these asymptotes, especially down here. All right, now let's think about that first asymptote, what it represented on that parent function of cosecant and where it is now. So this is that main reflection of our parent function. Well, we've basically taken that very first asymptote, this one right here, and we've moved it to the left, which means we're going to start with this downward facing parabolic shape. So I'm going to take from the between negative 2 pi and 0, that maximum for that parabolic shape is going to be negative 2, and then it's going to open down. And then the next one between 0 and 2 pi is pi, and that's going to be or have a minimum at 6 for that parabolic shape. And then I'm just going to continue this pattern. So halfway between 2 pi and 4 pi, we're at negative 2. Yeah. Halfway between 4 pi and 6 pi, we're at positive 6. And so on and so forth.